We're going to start today with a little intermission to remind us about some things that have gone on in the class so far. So now, at this point, we've encountered a whole bunch of different types of integration. And so it's a good idea to step back a little bit and organize those and remember what fits into what case and so on. So we've got two basic types of integrals in this class. We've got ones that tell us the total amount, like calculations for arc length, surface area, volume, and mass. And we've got integrals that tell us about total change, things like line integrals and flux integrals. If you like to be informal, the first type of integral is the kind of unpleasant one where we're always taking absolute values of things or lengths of things and stuff like that. The second kind is the kind that's a little bit more palatable, and there's lots of tools for manipulating it and changing them to different types of integrals. And the type of integral we get is going to depend on a question about what ambient dimension we're working in and what type of shape we're integrating over. So let's write up a couple of tables. So first of all, we can break down all the integrals we've got into integrating with respect to total amount or total change. And we've got a dimension we're working in. We could be working in classical single variable calculus in one dimension, or we could be doing stuff in 2D or 3D. And we could be integrating over a curve or over a surface or over a solid in 3D. And some of these combinations don't make sense. There are no surfaces inside one dimension. There are no solids inside 1D or 2D, and so we don't have to worry about those types of things. But within each of these, we've got a regular type of integral. So we can integrate a function over an interval in 1D, or we can do a double integral in 2D or a triple integral in 3D. Those are when we're integrating over solid, thick regions inside space. But for the types of integrals we're talking about, one way to think about the ones on the left-hand side is that they're a little bit more closely aligned with two-dimensional and three-dimensional change of coordinate formulas because they involve an absolute value of the determinant of the Jacobian. When we're integrating over a curve, the 2D and 3D integrals tell us about arc length or mass of wires. And in 2D or 3D, the ones where we integrate a vector field tell us about line integrals. Whereas when we're talking about integrating over surfaces in 3D, the integrals we did last week, we've got ones that tell us about surface area and mass, and we've got ones that tell us about flow of vector fields. So that gives us a kind of complete enumeration of all the different types of integration we know how to do, and just remembering what goes where and what formulas go with it is part of what's going on. And for notation, we've got a bunch of different ways to write all this stuff. So for example, we've got classical integration, we've got integration with respect to area, and triple integration with respect to volume over shapes and regions inside 2D and 3D. And in a arc length or mass version, we can integrate a scalar function over a curve, or we can integrate a scalar function over a surface. And we usually write those as d little s and d capital S. And I didn't make up the notation, I'm sorry. Whereas for these total change integrals, we still write the ones over regions in basically the same way. For line integrals, we write them as an integral of a vector field dot ds, and for our surface integrals, we write them as an integral of a vector field dot d capital S.